All right, am I on? I am on. Let's hope that the microphone stays on today. So welcome to Data 8, Lecture 35. Today we're going to be talking about classification. I have a bunch of announcements. So homework 7 is due tonight at midnight. Make sure you have that in. Project 3 is released. It goes over classification. You're going to be building your own classifier, and I'm going to be talking about what that is today. The checkpoint for Project 3 is due on Friday, and the entire project is due on Tuesday of next week. The final for this class will be held next Thursday from 2 to 5 p.m. So it'll be 2 to 5 p.m. It'll probably be in the data labs again, but we'll email you and post on Piazza the room assignments for the final as well. Because of that, the labs for next week will all be final review sessions. So there'll be like office hour style things where you can come in and ask questions about topics from the class or topics or problems that you've been working on. So there's no lab assignments for next week, but your labs instead will be final review. Lecture next week will also be final review. So lectures on Monday, Tuesday, and Wednesday of next week will all be reviewing concepts from the class to get you prepared for the final. Any questions about that? All right, we're almost done. Got like a week and a couple of days left. Hope you're excited. So today I'm pretty happy to introduce to you guys this topic called classification. So we're kind of in the middle of our discussion on prediction. Right? Given some data, can I make predictions about data that I haven't seen before, or can I make predictions about the world? We've seen examples of prediction for the past week or so when we talked about regression. And in regression, the way regression works is if we have some numerical data and we're trying to predict some other numerical data, we can use linear regression as a way to kind of make those predictions. Okay. So for example, if I wanted to predict how much an apartment in Berkeley would cost, given how many people are living in Berkeley for the past year, you could probably do a linear regression there and get some prediction for how much housing would cost in Berkeley. Turns out it's kind of a lot. But maybe if there's less people living in Berkeley, then housing prices will go down and vice versa. Okay, so that's an example of regression, and we've seen that before. Today we're going to be talking about a different type of prediction problem, and one that is really fundamental to machine learning as an entire field, basically. This problem is called classification. It's pretty similar to regression in that you're given some data and you're trying to make predictions. The only difference between classification and regression is that in classification, your predictions are categorical and not numerical. So Gmail is pretty good at getting spam out of your inbox, right? Pretty good. But for a long time, if you had an email address or email like inbox for a while, you'll note that like 10 years ago, your email inbox was probably like flooded with spam from all sorts of different places, and people eventually got like better and better at filtering out spam, right? So in the case, this classification is given some text in the email. Is this email spam or not? Should I put it in your inbox or not? So that was a problem that Google and other people had concerned themselves about for a long time. Right now, Google claims to have reduced the amount of spam in your inbox to about, it claims to have, like your inbox is probably like 99.9% good emails and like only 0.1% spam emails. And it's getting better at it because it has data to train on as you like get more and more emails. So for example, in this case, you could say, oh, this email has a word Viagra in it like 20 times. It's probably spam, and like they'll put it in the spam folder. An example of a classification problem. Another example of a classification problem is, for example, in self-driving cars, when they get a picture, so what they do is they put a camera on a car, and the camera has a video of the world, right, of what the car can see. And the basic idea is, okay, what should the car do? And given the image from the video, this thing right here is a car, this thing right here is a car, so don't hit those things. But this black stuff on the bottom here is the ground. You should roll over that to get to where you need to go. So that's another example of a classification problem. In this case, the input to the classification problem is the image, and the output is what stuff is in the image. Does this image contain a car? Does this image contain a person? All that stuff. Okay. Another example is, given an image of some medical scan, does this person, like, for example, this, I don't know what this is. I think it's just an image I pulled off Google. So this is not really a real image here. But you could say, given some x-rays or given some scan of a person's body, does this person have some sort of disease? In particular, like, for example, when you're looking at cancer, you're looking at tumors. And oftentimes you can tell from like the way the tumor looks, like the shape of it or whatever, different attributes of it, whether or not that tumor is cancerous or not. Okay, so it's a really important problem in the medical field. Another time classification comes up was in the past elections. So if you've heard of the Brexit election as well as the US presidential election, it turns out that there was a company there that was kind of looking at voter and voting trends. And what they were trying to do is they're trying to get people to vote some particular way, right? So they're like, okay, I want my party to win, or I want this candidate to win. So I'm going to try to get people to vote a certain way. What kinds of messages should I send people so that they'll listen to my message and hopefully change their mind about who they're going to vote for? So this case was particularly interesting because there was a company here that did the same sort of voter analysis for both people in the Brexit elections and people in the US presidential elections. And the difference that they did there was, instead of just looking at demographic information about like where you lived or how old you were and all of that, they try to get some more personal data about you. Like, for example, like some online, like your online profiles, like things you posted on publicly, things data they can get access to from your online presence. And they try to guess from there your personality. So attributes of your personality, like whether or not you're an introvert or an extrovert, whether or not like you're leaning left or leaning right, like politically. They try to get all those attributes out of you based on like the data you leave behind on the internet. They try to classify voters into like those broad categories, and then they try to tailor messages to specific groups of voters in that way. So in this case, the classification problem is, given some data about a person, like this person visited this website and like commented this thing, what can I conclude about that person's personality? So kind of creepy, but they did it. So classification comes up in a lot of different ways. Another example is fraud. So for example, when you're using credit cards, sometimes like your bank will call you and say, hey, you spent like $1,000 on this thing, did you do it? And they'll like shut down your credit card because they're afraid that someone else is using your credit card, right? So input there is credit card transaction, like location of it, how much you spent on it, all that stuff. And they're trying to classify whether or not your transaction was fraudulent or not. Another example is in online dating. So when two people sign up on the online dating site is trying to say, okay, will these two people like go together, like have fun on a date or not? Other classification examples. Another one is, for example, so classification is something you kind of do in your daily life as well, whether or not you know it. So for example, when I go to the grocery store, I look through the fruit. I'm like, which fruits will taste good? And I go to the mango section because I really like mangoes. And I'm like, okay, this mango is squishy, so it probably will taste good. This mango is like really hard, so maybe not. This mango smells right. So there's different attributes about some particular thing. And I use a combination of those attributes to make a judgment call about whether or not I will want to buy this mango or not. In a similar way, all these problems share that same kind of problem statement, where we have attributes about our input data, and we can try to make a prediction or classification about what that data is actually. Okay, so let me show you another example. All right. So I have here a bunch of stuff because I have a little nifty demo I'm going to show at the end. So I have data here on chronic kidney disease. Okay. And what we have here is data about individual people who did or did not have chronic kidney disease. So this is data from a blood test of people. This person was 48 years of age, there's blood pressure, specific gravity, don't know what that means, albumin, sugar, all this stuff. And at the very end here, we have whether or not they had chronic kidney disease or not. So this is kind of our input data. The basic idea of classification is we have some data that we already know the attributes about and whether or not like they've had this thing, whether or not they've had chronic kidney disease or not. Then we can say, okay, we have this data, and we can try to use a computer to find some patterns in this data. Then we can hopefully say, in the future, if I get more data about a person, and I don't know whether that person already has chronic kidney disease or not, I should be able to categorize that person, or make a prediction about that person. So this is our input data. We have a bunch of data here. Let's take a look at how many of them had disease and how many didn't. So we have here 43 people had chronic kidney disease, 150 people didn't. If I scatter plot the glucose level on the white blood cell count level, we can see here that this is what the data look like. So the yellow dots are people who had the disease, blue dots are people who did not have the disease. Look at this plot and come up with some way to distinguish between people who have chronic kidney disease and not. Talk it over with your neighbor.
So I guess if you have a new person having a white blood cell
All right, so how many guys think, no, I can't make a decision between people with disease and without? Okay, no. How many guys think, yes, I can? How many guys think maybe? Maybe. So interesting. So we look at this plot, right? And we're like, it seems like if I have a glucose and white blood cell count in this region over here, it looks like more likely than not that I won't have the disease. And if I get something way out here, way down here, I probably do have the disease, right? But if you look at this region right here, you'll notice that there are not just blue dots here, there are also yellow dots. So even if I go here and say, okay, if you have a white blood cell count of below this and a glucose count of below that, it seems like even if I make those rules, I will not be able to get a perfect classification, right? I'll say some people who have the disease do not have the disease. Now, oftentimes in classification, you won't be able to make perfect separations of who has and who has not. But oftentimes, just being good or mostly correct is good enough. It's useful. It's better than not being able to make the judgment call at all. So in this case, we could say, okay, it looks like all the blues are in this area. So I can say, okay, if your white blood cell count is above this line here and below, or white blood cell count is below this line here and below this line here, then you probably don't have the disease. And if it's somewhere else, then you probably do. You could probably write something like that. And it looks like here you get something that's reasonably accurate, right? Most of the points here are blue. All the points out here are yellow. But we have a bunch of other variables. So here we're just trying to say, OK, based on some two variables here, like this one, and glucose, which is somewhere else. Here it is. We have a bunch of other variables. So we can take a look at those other variables. Let's take a look at hemoglobin and glucose. What about now? What do you think? Talk it over with your neighbor. All right, so now how many guys think no, we can't make a decision? How many guys think maybe? How many guys think yes? All right, so indeed, you look at this and you're like, this does seem better than what I had before, right? Because before I had not a super hard and fast separation between blue and yellow, but here we can say, okay, it looks like if your hemoglobin is above this line and your glucose is below this line here, then it's almost certain that you won't have the disease, whereas if it's something else, it looks like you do. So depending on the two variables you look at, it becomes easier or harder to do the classification. Now, of course, you look at this and you're like, well, I'm only looking at a total of, well, there's 3 variables here, but I have I don't know how many there are here, maybe 30 or so variables here. Is there a way to combine all those things together to make a judgment call? And there is, but I won't go over it today. I'm just going to show you. I'm just trying to get you thinking about the ideas of classification. Okay. So contrast this with regression, which we talked about last week. In regression, we didn't have these blue dots and yellow dots. All we had was some points, and we were trying to say, okay, based on some x value, let me make a prediction for another variable. Here we have a couple of different variables, so hemoglobin and glucose. And we're not trying to make a numerical prediction, even though these are zeros and ones. The 0 and 1 here are categorical, right? They're saying you either have this disease or you don't have this disease. And what we're trying to do here is we're trying to say, okay, based on these two variables, what's the chance that you have the disease given you're out here or given that you're down here? Okay, so I have here another example. This example is on banknotes. So I don't think I have to tell you guys that some people carry around paper money, and paper money is useful for making purchases. So it's so useful, in fact, that some people try to counterfeit this paper money. And what they do is they try to make copies of it, And if it's believable enough, then when they give it to other people, they'll give them goods and services in exchange for their fake money. They're just pieces of paper, right? And what banks try to do is they try to collect both the real bills and the fake bills. And they try to say, OK, is there a way that I can distinguish between the real bills and the fake bills? And if so, then I'm trying to make the real bills harder to counterfeit so that the people are less likely to be bamboozled by these counterfeiters. Okay, so we have here some data on banknotes. Now this here, like these variables here are kind of hard to interpret. These are kind of strange image processing mathematical techniques here that I'm not going to go into. But basically what they did here is they took pictures of bills that were both fake and real. And what they did was they try to get out some attributes of that picture. In this case, we have this interesting attribute called wavelet variance, wavelet skew, wavelet kurtosis, the entropy of the picture. But all that is to say, these are some attributes that we think will be useful to help us decide whether or not this bill is real or not. And we have here the class. The class is 0 if the bill was real and 1 if the bill was counterfeit. Let's take a look at those two variables. So here I have the wavelet kurtosis on the wavelet variance. What do you think about this plot? So stare at it. And it looks like it's kind of hard to make a judgment call for this, right? You could say something like, OK, if you're above this line here and like below and like to the left of this line here, then you're definitely counterfeit. But once you get into this region here, you're not super sure. But if you get like beyond this diagonal looking line here, then you're almost certainly a real bill. So you could come up with rules like that, and it seems like it's kind of hard to make a judgment call there. What about another two variables? So let's try these two. So entropy versus wavelet skew. So you look at that and you're like, I don't know about this one either, right? It's kind of hard to make those, OK, like if you're above this, below this, then you're probably like a real bill or not, because you have like these weird looking patterns here. But you look at this and you're like, well, I can still kind of see some shape to the data, right? It looks like most of my counterfeit bills follow this kind of curvy looking shape over here, and most of my real bills follow this curvy looking shape there. Maybe there's a way to distinguish between the two. And the way that we can do that is, so I'm going to do this cool thing to make a 3-dimensional plot. OK, let's see if this will work. Whoa. It's unfortunately, let me see if I can. No, it's not centering itself. OK, well, let me see. What happens if I refresh? Oh, no. Refresh this thing. No. Oh, gosh. OK, wait. Refresh. Maybe it'll center itself after I refresh. So what I'm trying to show here is we have a couple of variables. When we plot each variable by itself, or when we compare two variables at a time, we're not able to see a clear separation between real and fake bills. But if I put 3 variables onto, oh nice, look at that, onto a 3-dimensional scatter plot, now let me rotate this around. Aha, if you look at that, you can get a separation there, right? There's some clear separation between the variables in 3 dimensions, right? Before I was looking at it only like this way. So if I looked at it like straight on like this is kind of equivalent to what we're looking at up here with the scatter plots in 2 dimensions. But when I plot the variables in 3 dimensions, then you can kind of rotate it some more and say, if I make some interesting rule here with like the diagonal line in this 3-dimensional space, then I can kind of separate out the fake bills from the real bills. So in general, oftentimes it'll be hard to look at just 2 variables and make a judgment call. But if you look at more and more variables, eventually, hopefully, the hope is that you will be able to find some way of distinguishing between your 2 classes. Any questions about that? Yeah, Sean?
Where are you getting the third line?
Where am I getting the, sorry?
Like the third interceptor, the third.
Oh, the 3rd dimension here?
Yeah.
Well, OK, if I zoom out a little bit, maybe it'll be more visible. OK, so here I'm plotting wavelet variance on the x-axis, wavelet skew on the y-axis, and wavelet kurtosis on the z-axis. So these were numbers from my original data. So here I have these 3 variables. In these scatter plots, I only plotted 2 of them. And so I got a two-dimensional scatter plot. If I plot all three at once, then I get a three-dimensional scatter plot. If I plot four variables, I get a four-dimensional scatter plot, which is hard to visualize. Yeah. But here we go. All right. And so you look at this and you're like, OK, seems like I can make a judgment call there. But the problem with what I've been describing so far is that all the ways that we've been distinguishing between the two classes are very specific to that problem. Right? So in this case, let's go back up to the kidney disease. So in this case, I said, OK, for this particular problem, if my hemoglobin is above 13 and the glucose is below 150, then you shouldn't have chronic kidney disease, right? And if I scroll down here, I have to go look at the data again, right? Plot the data again, and then make some judgment call again, looking at those points. Like, OK, if you're above like this particular like number and weightless skew and then variance and whatever, like kind of come up with those rules myself. Coming up with those rules myself means that the rules that I create will be very specific to this particular problem. So you can imagine yourself going through a bunch of data sets, a bunch of classification problems, and like coming up with those rules yourself. But you'll notice that coming up with those rules yourself is, one, not always easy, because we can't visualize things in more than 3 dimensions. So you can imagine that maybe in 3 dimensions, these variables are still hard to separate. But if I add a fourth variable, maybe it's easy to separate when I add a fourth variable. But I can't visualize that as a human being because I don't live in 4 dimensions. Or maybe I do. So what we're trying to do is, in classification, we're trying to say, OK, it looks like there's some properties in common between those two problems. We notice the common things about both of them. In both cases, we have some attributes. We have some attributes here, the age, blood pressure, specific gravity. Down here, we have the skew, kurtosis, whatever these are. It doesn't really matter what those attributes are, as long as those attributes let us distinguish between our different classes. So whatever our classes are. In this case, our classes are zeros and ones. And so when we notice that particular pattern in our problem, we think to ourselves, OK, it seems likely that there is a way of writing some kind of computer program for us without us having to go in and make the scatter plot and like make the hard and fast rules ourselves. Instead, we can say, OK, computer, figure out how to separate these points. Figure out which variables separate out the points, and you figure out how to classify new data. And I won't want to have to go in and look at these two variables and decide for myself which variables are important. I want the computer to be able to decide so that I can write one algorithm, one type of program to solve both these problems at once. And the reason why I can do that is because there's lots of properties in common with both these problems. So they seem very different. One of them is for kidney disease. One of them is for banknotes. But I propose to you that there is a way of taking the common properties of these problems and writing a computer program that can solve both of them. Yeah.
So this is individual, and it's not obvious which class they fall into. No, you have to like find like the closest distance to a point on the scatter plot if it's like not obvious.
Sorry. If you're saying if I have a new point come in and it's like way out here.
And it's like not obvious which clump it falls into.
Oh, so you're saying if I get a point on the border here, how would I decide?
You decide if it's like nearest point or what? Like closest point?
So I haven't talked about that yet. We'll talk about it tomorrow. Yeah. But I propose here there is a way. And the way that we do this, so we're going to be talking about this basically all day tomorrow when John comes in and gives his guest lecture. The way that we do this is to create something called a classifier. But I'm going to take attendance first. All right. And go ahead. Here's a link.
Sure.
Okay, so today I've shown you two different types of problems, two different types of classification problems. And we've seen that if we look at the data individually, like we look at each data set individually and kind of look at the points and look at the variables and all that stuff, we can kind of come up with ourselves some rules about how to classify the points. But what we would like is a way to kind of write a program that not only works for the two problems that we saw today, but works for general classification problems. Any type of classification problem where I have some inputs and I'm trying to guess from those inputs what the class of my data are, that's a classification problem, and there is a way to write a program that can handle those types of problems for us. Those are called classifiers. The way a classifier works is we look at what's common to all the problems that we observed before. What's common is that all the problems have some attribute. So for example, if I'm shopping for mangoes, I have like the shape of the mango, how big the mango is, the softness of the mango, different attributes. And there is some way to create some classifier so that if I give it those attributes, it can predict whether or not that mango will be tasty or not to eat. So whether or not Sam will like the mango or not. Okay, so there's a label in my example. All I have to do is replace the attributes with different data and replace the labels with different meaning. So here I can instead say, put in the attributes about a person's blood test and predict for me whether or not the person has chronic kidney disease, or put in attributes of the banknote and predict whether or not the banknote is real or counterfeit. Okay. So what I'm trying to do here is create some sort of program that can, when I'm trying to predict, all I have to do is give it some different data, and it can make that prediction for me. Okay. I'm not going to tell you how to do that today, but John will come in tomorrow and tell you about how to do all of that stuff. In your project 3, you'll be creating one of these classifiers. So you'll be creating a classifier to classify song lyrics. So you're going to look at song lyrics, and based on the song lyrics, you're going to see if you can make a prediction about whether or not that song is hip-hop or country, whether it's a hip-hop song or a country song based on lyrics. Okay. Tomorrow, we're not going to be going over how to do exactly that. We're going to go over instead how to write the classification algorithm. We're going to apply it to a slightly different problem. But hopefully from tomorrow's lecture, you'll be able to see how to use that idea in your project for project 3. So in general, classification kind of ties back to inference in this way. We have here a population of all possible mangoes, let's say. So all possible mangoes in my population. But I only see some subset, some sample of those mangoes when I go shop at the supermarket. Okay? So I have here some sample of mangoes. What I'm trying to do there is say, OK, I notice these things about the subset of mangoes, my sample of mangoes. Can I use that sample, use that data to infer something about what I like about mangoes in general in the population? So I have here my samples and whether or not I like the mangoes or not. What we do in classification and machine learning is to separate out our data into what we call a training set and a test set. Okay? And what we do with this training set is we say, OK, I observe maybe like 100 mangoes, but I'm only going to pretend like I observe 70 of them. Based on those 70, I'm going to try to figure out which attributes were most useful for me to decide whether or not the mango was tasty. Okay, so this is my training set. I'm going to train myself to figure out how to eat mangoes or like mangoes. In my test set, what I'm going to do there is say, OK, I'm not going to use those mangoes for deciding which parts of the mango I like the most. I'm going to use my test set to evaluate my accuracy. So what I'm doing there is I'm saying, OK, this particular set of data right here, I'm setting aside. I'm not using it to decide whether or not I like mangoes. So that after I figure out, OK, I like mangoes that are squishy. I like mangoes that are yellow. I like mangoes that are big, all that stuff. Once I figure out all that stuff, then I'm going to go over to my test set and say, OK, if I didn't know the label of this mango, would I have found it tasty or not? And what would I have said? And would I have been right? What would my accuracy be on the data that I haven't seen before? So the reason why we separate out our data into a training set and a test set is so that we can simulate more accurately the idea that in the real world, we're going to get stuff from the population that we don't know the label of. So we come in, we get a new mango that comes in. We don't know the label of that new mango. And we want to be able to say, OK, if I had never seen this data before, will my accuracy be? And that's the reason why we're going to split up our data into a training set and a test set. So there's some details there that may be unclear to you, but hopefully tomorrow with some more explanation, they'll be more clear. That's all I got for today. It's an introduction to classification. I will see you guys tomorrow.